What's a relational database? And what do we mean by a relational model? What's the difference between relational algebra and SQL? What are the most common operations in relational algebra and how can we combine them together to find what we're looking for? And what does relational algebra have to do with query optimization? Let's find out the answer to all these questions and more in this video. Hello and welcome. My name is Elhelw. I'm starting a series of videos to explain the internals of relational database systems. And what a better way to start than start talking about relational databases and what they are. So let's start with that. What is a database? A database is just a collection of data. It could be stored in any format. It could be a text file. It could be a spreadsheet. It could be in any way that you can store your data. There's a difference between databases and database management systems. Usually they're used interchangeably, but there is some kind of like subtle difference between them. A database management system is a software that allows you to manage your data, be able to manipulate that data, retrieve it, issue queries on that data. Some of the most popular and famous database management systems are things like Oracle, Microsoft SQL Server, Postgres, MySQL, and so on and so forth. There are different kinds of database management systems, but we are now going to focus on a kind that is known as a relational database management system, or let's just call it a relational database for short. What is that? A relational database is a database or database management system that follows and supports the relational model. Well, what is the relational model? The relational model is basically an abstraction, a way for us to kind of like conceptualize about a database and the data stored inside the database. How is the data stored? How is it organized? How are we able to access this data? How do we see the structure of the data? In the relational model, data is stored as relations. What's a relation? A relation is basically a representation of a type of objects or entities with all the different attributes that these objects can have. The physical storage of a relation is not part of a relational model. This is like an implementation detail that can be done differently in any system, but they all share the way that we see the data and the way that we interact with the data. It's also worth mentioning that even though the relational database systems, they follow the relational model, there are some subtle differences between the way they implement the relational model and the way it is defined in theory and in the research. And we'll point out these differences as we go. So as I said, a relation is kind of like the unit of the relational model, and it represents a kind of objects or entities that are all similar. They all have the same set of attributes. It is worth mentioning also that relations follow set semantics. And when I say that, I mean that the entries inside the relation, they cannot have duplicates, just like any set. When you're talking about set algebra, you cannot have any repetition inside the set. And also the order of objects within the set is not significant. This is what the relational model says. As I said, there are differences between the relational model as a theory and how database systems are implemented. In database systems, they allow duplicates usually, and the order can be significant. But in the abstract relational model, this is the case. Inside the relation, each object is represented as what we call a tuple. So a tuple is a representation of a single object within the relation, and it has all the attributes that are represented by this relation. So if we look at this example here, we have a relation called car. It represents all objects of type car, and each car would have the make, model, year, color, kind of transmission, etc., etc. This is an example of what would the objects look like. So when we populate this relation, we'll have, each object you can kind of like represent it as a row in this table that fills in the values for these attributes. The values are usually atomic or scalar values, like you could have strings, you could have integers, you could have double, dates, and so on and so forth. Again, this is what the relational model says. Many modern database systems allow for more complex types like arrays or like nested objects and so on. However, in the relational model, it just deals with objects as atomic values. You cannot have like, nested objects or anything like that. Also, usually every relation will specify what is called a primary key. This is either one attribute or more than one attribute that can uniquely identify a tuple. So this means that the values in the primary keys are unique for every tuple in that relation. You cannot have two tuples with the same primary key value. If it's a single attribute, then all the attributes in that, all the values in that attribute have to be different. If it's a combination of attributes, then those combinations have to be different for all the tuples in the relation. This is something that you can define when you specify your relation, or in some systems they can kind of like specify an automatic attribute as the primary key. It can usually be like a hidden attribute or something like that. And the way we denote this in the relational model is by having an underlined attribute in the relation specification. In this case, we have the ID attribute. This is the primary key. It has an underline. Let me go over some terminology so that we're clear on the terms that I'm using. When we talk about relation, I can also say table. Those are usually used interchangeably. Same thing with tuple, can also be referred to as a record or as a row in the table. So if you hear me use any of these terms, you know what I mean. When we talk about attributes, we also kind of like sometimes refer to them as columns or fields, because these are usually the columns in the table. So again, just be aware of all these different names that can be used in place of each other. Now, in order to interact with this data, interact with these relations, we need some kind of language. We need some kind of operations that we can perform on these relations. This is where relational algebra comes in. So relational algebra is basically a set of operations that we can apply on relations to combine them or to manipulate them in different ways to obtain a certain result that we're looking for. You can think of this as an analogy to the regular algebra that we have on numbers. When you have things like addition, subtraction, multiplication, division, and so on. So all these different operations that you can manipulate values to come up with a different value at the end. In this case, each of these operations takes a number or bunch of numbers as its input and then produces a number as the output. Same thing applies for relational algebra. Each operation in relational algebra takes one or more relations as its input and then produces a relation as the output. What is the importance of this? Why am I emphasizing this point? The fact that it takes relations as inputs and produces relations as outputs means that you can compose or chain multiple operations in a row. So you would have operation number one takes relations, produces another relation. That output relation can be used as an input for another operation, and so on and so forth. So you can compose or chain multiple operations to produce some complex expression. Again, this is the same as you do in numerical algebra. You can compose addition and multiplication and subtraction. You can have multiple nested level of operations, and the output of one operation is the input to the next operation, and so on and so forth. Relational algebra is seen as the basis for a language like SQL. SQL, I'm sure most of you are familiar with that. It's the language that we use to manipulate data in database systems. It's built on relational algebra. However, there are some differences. Again, we'll point these out as we go. Relational algebra as a concept or a conceptual language is procedural. Procedural in the sense that you specify the order of operations to evaluate. Again, same thing as you do in an arithmetic expression, right? You have a certain order of operations, and you can use parentheses to say which operation you want to specify first. Same thing in relational algebra. You specify the order of the operations to evaluate. Since it's part of the relational model, it's also based on set semantics. This means that there are no duplicates allowed anywhere. If some operation produces duplicates, these will be eliminated automatically. So you will never have any duplicates at any part of a relational algebra expression. SQL is a little different because it's non-procedural, or what we call declarative, which means that you don't really specify the order of the operations. You just specify what you're looking for, and then the database system, specifically the query optimizer, will figure out the most efficient way to do this. It might change the order of operations, it might do some manipulation, it might replace an operation with something else. So you don't really specify how to evaluate an expression, but in relational algebra, the order of operations is significant. We're going to talk about some of the most common operations in relational algebra. These are namely selection, rename, projection, union, intersection, difference, and then we're going to talk about product and join. There are multiple other operations that are out there, but these are the main ones that we're going to focus on in this video. So let's start with selection. Selection is an operation that is usually denoted as the Greek sigma letter, and basically it outputs tuples that satisfy a certain condition. You specify this condition as you're writing the selection. You can combine multiple conditions with ands and ors and whatnot, so you can have multiple conjunctions or disjunctions in your condition. And it is written as sigma with the condition or conditions in the subscript, and then you apply this to some input. And as I said, the input has to be a relation. This could be like a base relation or the output of another operation. Let's illustrate this with an example. Suppose we have the car table, kind of like a smaller version of the car table that we've seen earlier. It has 3 attributes. It has ID, make, and year, and here ID is the primary key, and it has 4 tuples. So if we apply some selection on that, let's say we do a selection with the condition that make equals Toyota. This means that we want to select only the tuples that satisfy this condition. So the output of that operation will be another relation that has only those 2 tuples. Similarly, if we want to evaluate like a multiple conditions with AND, so we can do something like this: select where make equals Toyota and year is greater than less than 2020. So these are 2 conditions that we join together with an AND. So now we only select the tuple that satisfy both conditions. So in this case, the output is a relation with a single tuple that satisfies both conditions. This is one of the most basic operations that is used everywhere to kind of like, narrow down the set of tuples that you're dealing with. The next operation we're going to talk about is the rename operation. Many of us may not be familiar with it. It might be kind of like, one of the less popular operations, but it has many uses, as we will see in this video. This operation, basically, it outputs a relation with renamed attributes. What does that mean? The syntax looks like this. It has row, the Greek row symbol, and a bunch of attribute names. And then, again, you apply this to the input that you have. In this case, again, we have the car table. Now we want to apply this rename on it. So we're going to say rename, ID, brand, year, apply this to the table car. So basically, we are changing the name of the middle attribute. Instead of make, we're going to change it to brand. So the output will be the exact same relation. However, the second attribute has been renamed to brand. This does not change the car relation anyway. Like the car relation is as is. This is the output of the operation has a different attribute name. The third operation is projection. So projection also has to do with attributes, but it's basically you're specifying certain attributes that you want to include in the output. This is different from rename. Rename takes all the attributes, but it renames some of them. This one may add more attributes, may remove attributes, may change the order of attributes. This is represented by the symbol pi, and you give it the list of attributes that you want to output. The attributes here can also include expressions, as we will see in some of the following examples, but we'll get to that. Let's start with a simple example to illustrate the simple case. So again, we're starting with the car relation or the car table that we have with 3 attributes, ID, make, and year. Now we're going to say, I want a projection of only the year and make attributes. And this will be the output. What did we do here? First of all, we did not include the ID attribute. We only included year and make, and we also put year before make in the output. So the input is the table car, and then the output is this new table that has only 2 attributes, year and make. Let's see another example. We could do something like this. We could do a projection of make and year plus 1. Note here, the second attribute is actually an arithmetic expression, or could be any kind of expression, could be a string expression depending on the attributes that we have. What does this mean? It means that for every tuple, you're going to evaluate that expression, and you're going to put the value or the output of that. So the output would look like this. The make attribute is just copied as is. The year attribute for every tuple has been increased by 1. So for the first tuple that has Toyota 2015, now in the output it has Toyota 2016. And the same applies for every tuple in that table. And also the attribute name in this case is not the original year attribute, it's a new attribute that's called year plus 1. So this is something that you can also do in projection if you want to apply some operation or some function on all the values of a particular attribute. The name year plus 1 is obviously not great and not super convenient if you want to, let's say, do some operations on that later on. So you can change that name, and we've seen how. We can use the rename operator in this case. So we can do something like this. We can take this whole relation that is output of the projection and use that as an input to a rename operation. So we can do this, have a rename of this whole input and specify 2 attribute names. In this case, we're saying brand and next, for example. So the output will look like this. The same data, the same tuples from before, but the attribute names have been changed. Take care here with the order of the evaluation. So as we specified, like relational algebra specifies the order of evaluating the operations. In this particular case, we evaluate the projection first and then the rename second. Basically, in order to evaluate any operation, the inputs of that operation have to be already evaluated. Another example, again, starting from the car table or the car relation that we have. Now we're going to do projection. Now we're going to start with selection first, actually. We're going to select all the tuples that satisfy this condition. Year is equals 2015. This will give us these 2 tuples. We've seen selection in the beginning. But what if I don't want all the data? What if I want just the makes of the cars that satisfy this condition? Then I can also chain a projection after that and say, let's just project the make attribute, in which case the output will look like this. So now you see how you can chain or compose multiple operations to get the result that you're looking for. And you have to be careful with which operation executes first. Another example here, just to clarify one point that we mentioned earlier. Let's suppose we do this projection. We're projecting only the make column from the car relation. You think that you will get all 4 attributes just for the make column. However, one thing to note, as we mentioned, relational algebra follows the set semantics, which means you cannot have duplicate tuples. This output relation has 4 tuples. Each tuple has just 1 attribute. 2 of them are the same. So this cannot be the output. In this particular case, the output is actually going to be just these 3 tuples because the duplicate will be automatically removed. Again, this is not the same in SQL. In SQL or SQL, if you do this kind of query, you will still get 4 tuples. This is one of the differences between relational algebra and SQL. All right, now we're going to go to another kind of like group of operations that have multiple inputs. These operations are very similar to like the set operations that we're familiar with, like union operation, intersection, set difference, but these operate on relations. So let's start with the union. Union, basically you have 2 input relations, and you want to output all the tuples that appear in either one or both of those relations. And as usual, no duplicates are allowed. So if any tuple appears in both relations, it will only appear once in the output. It's not going to appear twice. One important condition is that the input relations must have the same attributes in order to be able to do a union on them. And the output will also have the same attributes. And this is how we write this operation. We just use the union symbol with the 2 input relations. So example, we have these 2 relations, S and R. Each has 2 attributes, ID and name, with some data in there. Notice that there is 1 tuple that is existing in both relations. So now if we want to make a union of them, the output will look like this. So R union S will have 5 tuples, not 6, because the duplicate has been eliminated. So anything that appears in R or S is part of the output. Let's look at a second example. Here we have R and S as well. However, the second attribute has a different name. As I mentioned earlier, we cannot do this in the union, the attributes must have, the relations must have the same attributes in order to be able to do a union operation on them. We cannot do R union S in this case because each of them has a different set of attributes. However, if we do want to do that, we can use the rename operation, for example, to change the attribute names so that they can match, and then we can do the union. So instead of saying R union S, we can do R union a rename of S using the ID and name column names. So now the right-hand side of the union produces ID and name, not ID and label, in which case both sides of the union are matching. Now we can do the union, and the output will look like this. So always remember how you can use the different operations to do what you want. If something doesn't work, you might have to use another operation on it to manipulate it a little bit before you can apply something like union, for example. Another example, here we have two operations that have different attributes. So one has ID, name, and country. The other has ID, name, and age. You don't have to union the whole relation. Sometimes you need just one part of the information. For example, let's say we want only the list of names from both these tables, right? We don't want to see the country, we don't want to see the age, we don't want to see the IDs, just the list of names. So we don't need to do this. We don't need to do R union S because, well, first, we don't need that information. Second, because it's not going to work because they have different attributes. But if we want just the names, then we can project the name from both sides. So we can project the name from R, project the name from S. This will produce two relations that have only a name attribute. Now both sides of the union are matching, and we can perform the union, and the output will look like this. Again, notice that all the duplicates have been removed in this case. The next operation is very similar. It's intersection instead of union. So now instead of outputting everything that appears on any of the input relations, you're only going to output things that appear in both relations. Again, same condition, both relations must have the same set of attributes, and we write this as input 1 intersection with input 2. Just to illustrate, now we have those same tables. They both have ID and name attributes. There is only one common tuple here, which the one that has ID 2 and name Bob. So the output of the intersection will be this single tuple. It's very straightforward, just like the intersection operation that we have in sets or anywhere else. The third operation in this group of operations is the difference. Again, similar to difference operation somewhere else, is basically the set of tuples that appear in the first relation but do not appear in the second relation. Same condition, they both need to have the same attributes, and we represent it using the difference operation like this. Again, to illustrate, we have these two relations. Same tuple appears in both sides. So the difference will be everything from the first relation that does not appear in the second. So if we do R difference S, the output will be everything that does not appear in S, which is the remaining two tuples in this case. Now we're going to move into a different kind of operation. The next operation is called the product. Sometimes we call it Cartesian product or cross product. This also has two inputs, but it combines them in different ways than we have seen in union or intersection, for example. Let's look at this example to see what that means. So first of all, the syntax looks like this, and then now we look at the example. So each tuple from the first relation is going to be combined with each tuple from the second relation. Kind of like think of it as a nested loops. Like you have one loop looping over the first relation, and then within that loop you have a loop that goes over the second relation and outputs a combination of both. So first tuple, we need to combine it with every single tuple from the second side, and then the same applies for the second and the third tuple on the first relation. The output looks like this. So basically you have all the attributes from R and all the attributes from S combined together into a larger relation. So you will see 1 and Alice from R have been combined with every single one from the S relation, and you have 3 attributes there, and then the same applies for every other attribute from R. The number of attributes in the output is basically the sum of the attributes from both relations. One thing to note here, the ID attribute, because we have ID coming from S and ID coming from R, so the name is ambiguous. In this case, we prefix that with the relation name that it came from. For name and location, there was no ambiguity, so we did not need to add any prefix there. So again, this operation just combines all different tuples coming from both sides. By itself, it might not be super useful. but this is the basis for a more useful operation, which is called the join, which is something that is used everywhere, and everyone has probably used that operation in some form or another. So let's talk about that. The join operation, in particularly the one we call inner join, because there are other kinds of join that we're not going to get into in this video. You might have heard of semi-join or outer join. So here we're talking about inner join. It's usually represented by this bow tie symbol. The syntax is like this. There are actually multiple syntaxes. The first one is you put the bow tie with some attributes. These are called the join attributes or join keys, and then you put the two inputs. And the meaning is that we're combining tuples from both sides that have equal values for these join attributes. What does that mean? So let's see that as an example. One also thing to note is that the join attributes are output only once in the output relation. But let's see that. So here we have R and S as relations, ID and name, and then ID and location on the other side. And we want to join them on the ID attribute. So the join attribute must be something that exists in both relations. You cannot, for example, join this on name because S does not have a name attribute. So it has to be something that exists on both sides. So in this case, it's ID. So this means I want to match the tuples that have the same value for ID. In this example, you have the value of 2 and the value of 3 exists on both sides. Anything that does not exist on both sides will not be part of the output. So the row that has 1 and Alice, there is no ID 1 on the other side, so that part is not going to be part of the output. The same thing for 5 and UK on the other side. So the output will look like this. Only IDs 2 and 3 are part of the output. For each of them, the ID value appears only once because that's the join column or join attribute. And then we put the rest of the fields from both sides. So we put the name and then the location. So we have ID Bob, ID 2, name Bob, location Canada, and so on. So this is the way that we combine related information coming from different relations. Another way to specify the join operation, instead of just specifying the join attributes or the join keys, you can actually specify a condition. Same way that we did in selection. And also, again, the condition can have ands and ors and whatever you want to put to combine multiple conditions together. This is like a more general form of the join syntax. And in this case, we combine the tuples that satisfy this condition. In this case, we're not mentioning a particular attribute, so you can actually join on different attributes from different relations, and then the ones that satisfy the condition will be part of the output. And in this particular case, all the attributes from both sides are part of the output. We don't eliminate anything. So if we look at these two tables here, let's say we want to replicate the same join that we did using the first syntax, but using the second one. So we can do it like this. We can say join where r.id equals s.id. In this case, again, here's the output. Notice that the ID column here is repeated, and we added the prefix to each side, and then the rest of the columns are there. And again, Alice did not appear, UK did not appear because they did not join with anything. That's the semantics of the inner join. This could also be represented as a product, the product operation that we mentioned earlier, which combines all the different combinations and then followed by a selection. So if we do a product followed by selection, this will be equivalent to the join that we did here. There are other operations that we'll not get into. These ones are kind of like the most common operations that we can combine in different ways to get the result that we're looking for. One common question that you might be asking yourself, we've seen multiple operations that take 2 inputs, like we've seen join on 2 inputs, we've seen union on 2 inputs, and so on. What do we do if we want to join 3 or more relations? What do we do if we want to union 3 or more relations? Simply, you just combine multiple operations. So you can do a union of 2 relations, take the output, put it into a union with a 3rd relation, take that output, union it with a 4th relation, and so on and so forth. So this is where chaining comes in, right? Same thing with join. You can join 2 relations, and then the output of that can be joined with a 3rd, and so on and so forth. Now, one important thing that I want to talk about is tree representation. There is a way to represent a relational algebra expression using trees. Before I get into relational algebra expression, let's see how we can do that for arithmetic expressions, right? So if you have an expression like this, x plus y, basic arithmetic addition, right? You can represent this as a tree where the operation is the root and the leaves or the children are the inputs, right? So it can look like this. X and Y are two inputs that are being combined using a plus or an addition operation. To evaluate any node, you must evaluate its children first, because the children are the inputs. So the inputs must first be evaluated before you can evaluate the parent node. You can use this representation to combine multiple operations and specifying the order. So let's say we want to multiply this output of x plus y, multiply that by z, right? Simply in the tree, this means that this whole thing will become a child of another operation. So it will look like this. So now you have the multiplication, has two children. One of them is the addition output, and then the other is z. This representation also specifies the order of evaluation, right? If we want to evaluate the multiplication, which is the root, we have to evaluate its child first, because we cannot multiply something where the child is an operation. You have to first evaluate that operation, get a result, and then do the multiplication. So the addition here will happen first, and once that is done, basically imagine that you're almost replacing this whole circle with a value. Then you can do the multiplication second, which corresponds to the parentheses that we have in the original expression. So the same thing, we can also apply that to relational algebra expressions. Let's illustrate that with an example to see how to do this. Suppose we have two relations. We have job relation that has job ID and title, and then we have a person relation that has a person ID, name, and job ID, so to indicate what job this person has. Now, what we're looking for, we want to return the name and job title for every person who is not a manager, right? So this is, imagine this is a query that you wanna write with the relational algebra. How do you think of this? So we want to return the name and the job, right? So somehow we want to combine things from different tables. But we don't want to combine all the different combinations. We want things that actually correspond to each other. So we're going to start with the person and the job relations, and we're going to join them using the job ID in this case. So this will combine the corresponding rows from person and job. What's the next step? We want only to output the ones that are not a manager, right? So that's a condition. So we can add a selection on top of that says title is not equal to a manager. So see here the order of operations. So the join is going to happen first, and then we're going to do the selection on top of it. Now, okay, we filtered out everyone who's a manager, and now we have the non-manager people are remaining. So are we done? Let's look at the query again. We want to return the name and the job. Currently, this will return all the attributes, right? So we want to specify which attributes we want. So this is a projection. So I will add a projection that says return the name and the title attributes. And this will be our expression. This is the tree form. Can we use this to write it in the regular kind of like, single line form? Let's see. Let's start from the first operation to execute, which is the join. So basically we write this as person join job using the job ID as the join key. The next operation will be the selection. So all of this join is going to be the input to the selection. So we write it like this. And then this whole thing is the input to the projection. So the expression looks at the end like this. So this is a way to represent relational algebra expressions as trees. Why is this important? Why am I even explaining this? Because later on in other videos, once we get to query optimization, the query optimizer deals with queries in this tree form. So the first thing it will do is that it will convert an SQL query to this tree representation, and then it will start manipulating the tree, replacing nodes with other nodes, changing the order of certain nodes, and so on. And then the final tree will be corresponding to the execution plan that will actually use to evaluate the query. As I mentioned earlier, like the tree also specifies the order of the operation. So this is the same tree that we've just seen. In here, we did the join first, and then we did the selection, right? Is this the only way to do it? No. We could have done it in a different way. Like we could have done the selection first on the jobs, so filter out the jobs that are, like filter out the manager, and then the remaining ones we're going to join those with the person table. So these are two different ways that will return the exact same results. However, each of these might have a different cost in terms of resources, in terms of memory, in terms of CPU and all that. And as you can see, each of these is written differently using the relational algebra expression, but these are equivalent. There are different transformations that, if you want to study more about relational algebra, you'll understand what transformations are valid, what are not valid, and this is the kind of stuff that the optimizer will do. Just a high level kind of idea of what the optimizer does. When you give it a SQL query or an SQL query, it will first construct a kind of an initial query tree, and then it will use all these transformation rules, like the valid transformation rules, to try to kind of generate more different trees that are equivalent to the original one. And then it will somehow figure out which one of these is the most efficient one, and then use that to run your query. We'll have separate video or videos on the query optimizer and how it actually performs these steps, but kind of this is the idea on a high level. That's why understanding relational algebra is very important. If you're someone who works in the database internals or in query optimization specifically, you need to understand how these queries are represented and what transformations are valid and what are not valid. If you're not someone who works in the internals of a database, like if you're someone who works at the application layer and writes queries, usually you just rely on the optimizer to take care of this. But know that optimizers are not perfect. Some optimizers, or not, actually every optimizer does not consider all possible transformations, because that's like an infinite set. So if your particular query happens to have some case where the optimizer does not consider a transformation, you might also know, okay, the query is not performing well. Maybe I can rewrite it in a different way before I even submit it to the database system, which will be equivalent to the original one, but will be kind of faster to run. So it's important to understand how relational algebra works, what the different operations are, what happens if I switch the order of these operations, and will I get the same result or not. So to summarize this video, we start talking about relational databases. We explained the relational model. What does it mean? How the data is represented in relations with attributes, and every object is corresponding to a tuple in that relation. We also kind of went over some of the differences between the relational model and the database management systems that are based on that, in terms of how the relational model follows the set semantics. For example, it does not have any duplicates, while relational databases, they do allow duplicates. They also do have a significance, or you can specify the order in certain operations, whereas the relational model does not have that. And the same difference also kind of is between the relational algebra and SQL. We talked about relational algebra as a conceptual way of manipulating and combining data that follows the relational model in order to turn certain type of results. The relational algebra, as we mentioned, is a procedural language, since you specify the order of evaluating the operations. Each operation takes relations as inputs, outputs also relations. You can chain or compose operations to have a more complex expression. We talked about some of the operations like selection, projection, join, product, and so on, union, intersection, all that. We also ended with explaining the tree representation of relational algebra expressions, how that can clearly show the order of evaluation. We have to evaluate children before we can evaluate the parent, and then the root node is the final result of the expression. And we also kind of went over how this representation is useful in query optimization. As I mentioned, we're going to go into the details of query optimization in other videos. I'm going to also be talking about other parts of the database system, like the storage layer, query execution, indexes, and all that. So if you'd like to get all that information, please subscribe to the channel. Also, I hope this video has been useful. If so, feel free to share it with other folks. Feel free to like it. If you have any particular topics that you would like me to talk about, please add them in the comments below. And with that, thanks again for watching, and see you next time.